Rocks form the physical foundation of the Earth's surface and play a fundamental role in shaping landscapes, ecosystems, and human activity. Although rocks may appear simple, they are composed of minerals whose composition and structure provide valuable information about the geological processes that have shaped the planet over billions of years. By studying these minerals, geologists are able to interpret how rocks form, the environments in which they develop, and the conditions that existed at different times in Earth's history. Minerals are naturally occurring inorganic solids with a definite chemical composition and a well-ordered internal crystal structure. When minerals occur in sufficient quantities to make up most of a rock, they are referred to as rock-forming minerals, although thousands of different minerals have been identified. Only a relatively small number are responsible for forming the majority of rocks found in the Earth's crust. These rock-forming minerals can be broadly grouped into silicate minerals and carbonate minerals, both of which are essential to understanding igneous, sedimentary, and metamorphic rocks. Silicate minerals are by far the most abundant group of minerals in the Earth's crust, accounting for more than 90% of its composition. All silicate minerals contain silicon and oxygen, often combined with other elements such as aluminium, iron, magnesium, calcium, sodium, or potassium. The fundamental building block of all silicate minerals is the silicon-oxygen tetrahedron, which consists of one silicon atom bonded to 4 oxygen atoms. These tetrahedra can link together in a variety of ways, forming chains, sheets, or three-dimensional frameworks. The way in which these tetrahedra are arranged determines the physical and chemical properties of each silicate mineral. One of the most important and abundant silicate mineral groups is feldspar. Feldspars make up approximately 60% of the Earth's crust and are found in most igneous, metamorphic, and some sedimentary rocks. They are aluminium-rich silicates that contain varying amounts of potassium, sodium, and calcium. Feldspars are generally light in color and are characterized by 2 planes of cleavage that intersect at nearly right angles. Plagioclase feldspar is one of the 2 main types of feldspar and forms a continuous series between sodium-rich and calcium-rich compositions. It is commonly found in igneous rocks, such as basalt, gabbro, and diorite, which are often associated with volcanic activity or magma that cools beneath the Earth's surface. Plagioclase feldspar typically appears white to gray and may show fine parallel lines, known as striations, on cleavage surfaces. The second major type of feldspar is alkali feldspar, which contains potassium and sodium. Alkali feldspar is commonly found in granite and rhyolite, rocks that form from silica-rich magma. These rocks are characteristic of continental crust and typically form in environments where magma cools slowly, allowing larger mineral crystals to develop. Alkali feldspar often appears pink, white, or cream in color, and is one of the most easily recognizable minerals in granite. Another extremely important silicate mineral is quartz. Quartz is composed entirely of silicon and oxygen, and has a strong 3-dimensional framework structure. This structure makes quartz hard, chemically stable, and highly resistant to weathering and erosion. As a result, quartz is one of the most common minerals found in sedimentary environments, particularly in sand and sandstone. Quartz grains can survive repeated cycles of erosion, transport, and deposition, making them a key component of many sedimentary rocks. Quartz occurs in a wide variety of forms and colors, including clear rock crystal, milky quartz, and colored varieties such as amethyst and citrine. Despite these variations, all quartz shares the same basic chemical composition. Because of its durability, quartz plays a significant role in shaping landscapes and coastlines and is a major component of many soils. Mica minerals are another important group of silicate minerals and are easily recognized by their distinctive sheet-like structure. This structure allows mica minerals to split into thin, flat layers, a property known as basal cleavage. Mica minerals are typically shiny and reflective, making them visually distinctive in many rocks. The 2 most common mica minerals are biotite and muscovite. Biotite is a dark-colored mica, rich in iron and magnesium, and is commonly found in igneous and metamorphic rocks. Muscovite, on the other hand, is a light-colored mica, rich in potassium and aluminium. Both types of mica are commonly found in granite and in metamorphic rocks, such as schist and gneiss. The presence of mica minerals often indicates slow cooling or metamorphic conditions that allow sheet structures to form. Amphibole and pyroxene are silicate minerals that are rich in iron and magnesium and are therefore often referred to as ferromagnesian minerals. These minerals are typically dark in color and form under high-temperature conditions. They are especially common in igneous rocks derived from magma originating deep within the Earth's mantle. Pyroxene minerals have a single-chain silicate structure and are commonly found in basalt and gabbro. These rocks are associated with volcanic regions and oceanic crust. Pyroxenes are important indicators of mafic rocks, which are rich in iron and magnesium and relatively low in silica. Amphibole minerals are similar in composition to pyroxenes, but have a different crystal structure, consisting of double chains of tetrahedra. This structural difference results in distinct physical properties, including different cleavage angles. A common amphibole mineral is hornblende, which typically appears dark green or black. Amphiboles are commonly found in intermediate igneous rocks such as diorite and in a variety of metamorphic rocks. Clay minerals are fine-grained silicate minerals that form primarily through the chemical weathering of feldspar and other silicate minerals. They are a major component of soils and sedimentary rocks such as shale. Because clay minerals are extremely small, they have a large surface area relative to their size, allowing them to retain water and nutrients. This property makes clay minerals particularly important for soil fertility, agriculture, and land use planning. Another significant silicate mineral is garnet. Garnet is most commonly found in metamorphic rocks and forms under conditions of high pressure and temperature. Garnet crystals are typically red or brown and have a distinctive well-formed crystal shape. Because garnet forms under specific metamorphic conditions, it is often used by geologists as an indicator mineral to determine the intensity of metamorphism that a rock has experienced. In contrast to silicate minerals, carbonate minerals are based on the carbonate ion, which contains carbon and oxygen. Carbonate minerals are particularly important in sedimentary environments and play a major role in the global carbon cycle. Two of the most important carbonate minerals are calcite and dolomite. Calcite is composed of calcium carbonate and is the principal mineral in limestone and chalk. These rocks commonly form from the accumulation of shells and skeletal material from marine organisms or through chemical precipitation in shallow seas. Calcite is relatively soft compared to many silicate minerals and reacts readily with weak acids, a property that makes it easy to identify in the field. Dolomite is composed of calcium, magnesium carbonate, and forms the rock dolostone. Dolomite is similar in appearance to calcite, but has a different chemical composition. It is commonly found in ancient marine environments and provides valuable information about past ocean chemistry and environmental conditions. The study of rock-forming minerals is essential for understanding the Earth's geological history. By identifying minerals and examining their composition and structure, geologists can classify rocks, interpret the environments in which they formed, and reconstruct past tectonic, climatic, and biological conditions. Rock-forming minerals also have practical importance as they influence soil development, landscape evolution, and the distribution of natural resources. In summary, the Earth's crust is composed primarily of a small number of key rock-forming minerals. Silicate minerals, particularly feldspar and quartz, dominate the crust and form the foundation of most igneous and metamorphic rocks. Carbonate minerals such as calcite and dolomite are central to sedimentary systems and the global carbon cycle. Together, these minerals provide a framework for understanding the processes that shape our planet and continue to influence the world we live in today.